Okay, so like I said, I'm Ryan. This is Rachid. So like all of you, who, so I said we work at NVIDIA. Like all of you, we um, at NVIDIA we like to put our GPUs into our data centers. Is everything okay with the mics? There we go. Okay.
Apologies for the.
That's okay. I'm trying to. Yeah, yeah. Oh, I lost the. I need the clicker though. Yeah, go back. That's perfect, right there. Thank you. Okay. So like all of you, you know, everyone who's using GPUs, so we like to put GPUs in our data centers, and we like to do things with them. We like to put software on it and see how they run, and find different things that we can do with them. And so that's what we're going to talk about today. Is actually our exploration, our team's exploration, and some work that we've done actually building a cloud within NVIDIA. And so the cloud that we are going to talk about has, perfect, thank you, has two types of workloads. So we've got game streaming and AI workloads. So the first one that we're going to mention is called GeForce Now. Has anyone heard of GeForce Now? A show of hands. Yes. Great. So game streaming. This is way I would describe GeForce Now for you is it's Netflix for gaming. This is what good short answer that Rachid gave me. That you could take a game and you could stream it for you. You can open a client, you can open a browser, and you can stream a game. And essentially what's happening on the back end is you're connecting to a data center, you're connecting to one of our data center GPUs, and we're giving you a slice of this GPU for a period of time so you can play your game. So essentially, like, you're getting what would be your like 4080 that you got under your desk. We can actually get access to something very similar in the cloud, like an L40G, and you can play your game on this. And so this is what we do as part of GeForce Now. So this is a big workload that we support in our GPU cloud, probably the primary workload. And the second one, a pretty new experience for us in our GPU cloud, I'm calling it, is NVIDIA Cloud Functions. So a very cool experience that we've been going through where we actually want to start supporting some AI inferencing workloads in our cloud. So Rachid will talk a little bit more about how these work and how these play inside of our clouds. So what is it? So this is a very high level architectural overview, and if you have more questions about the technicals of all this, reach us afterwards. I'll go through all of the pieces if you'd like. But high level, so we use Kubernetes 126. We've actually started our journey back. I think it was like Kubernetes 121 was the first version we deployed into our GPU GeForce Now cloud, and we've since upgraded it quite a few times, and we'll be going to 128 pretty soon. We use KubeVirt. So think about, we do game streaming, right? Run Windows guests. So we run those in virtual machines. And KubeVirt, if you don't know, KubeVirt is just a virtual machine layer on top of Kubernetes. It's under the hood. It's actually just a pod, right? That's the primary layer, that workload that Kubernetes provides, is a pod. And inside the pod is libvirt and QEMU, right? All the tools that you get when you want to run on a Linux hypervisor. And then on each of the hosts, we have KVM. So we have this interaction where we've got libvirt, QEMU, KVM working together to create this guest. And inside is the game streaming session, which is what GeForce Now is. Networking layer, we use Open Kubernetes, and we also use a bunch of other projects, but I'm just giving you the high level of what this looks like. Okay, and then a little bit about it. So our cloud, we've got tons of data centers. They're located all over the world. I mean, I even think this is out of date. I mean, we probably maybe even like 40 plus or 50 plus now. I think it's quite a few more. But we're geolocated all over the place, and so you can imagine, like, picture in your mind, like, we've got this service, we've got this large cloud, we've got a lot of GPUs, and so what are the problems? What are the things that we're facing? What are the challenges? And so that's what we're going to talk through today. Like, what are the challenges in the front of our minds today? Like, what are Rachid and I working through in our teams? And we'll talk through exactly how the different problems we face. So I'll hand off to you.
Mm-hmm. Which one is that? Okay.
Yeah, just the arrow there. Yep.
Hey everybody. So maybe a little bit of context. So just as Ryan was saying, in order to stream a game, which is our main use case today, is we run basically a game on one of those virtual machines. And can you? Okay, maybe I speak up a little bit. So well, I was saying that in order to stream a game, we're basically running a game on a virtual machine in our data center, and then we leverage our streaming magic that streams. So it's different from streaming a movie or music. We're leveraging NVIDIA technology called GameStream. So that streams the game from that machine to the user's device, and then it also streams the input from the user to the machine. So with games, users control like a car or something. So we leverage this technology. So this is one of like the magic that we have that allows for game streaming. So one of the, other than the streaming protocol that we leverage, so one of the challenges that we have is how do we connect the user to that virtual machine that's running in a data center. And it's especially for gamers, they will tell you if they see a frame drop. So it's important to us that we provide the optimal quality for the end user. So it should seem like the user is playing the game on their local machine. And yeah, this is one of the main primary responsibilities, to connect the data center to the user. So the way we did this is we introduced an NVIDIA scheduler. So this sits very close to the Kubernetes cluster that Ryan was talking about. And what it does is it takes a bunch of input. Some of it comes from the user. Some of it comes from, or is derived from business rules that our business unit came up with. And some of it is also input, but also the state of the DC within the region, the data center where the user closest to. So I'll go through them one by one. So when the user tries to play a game, so focusing here more on the gaming use case. So when the user tries to play a game, one of the input is the user location. So like I mentioned, low latency is extremely important for gaming. Imagine you're playing a racing game or Formula One or something. You want to make sure that things move very fast, so latency is extremely important. So one thing we do is, on top of the, what's it called, the location-based routing that we do, so we direct you to the closest data center. If you play GeForce now, you'll notice that the user interface will ask for a latency test between the client and different data centers in the same region. So, for example, we're here in New York. If we try to play a game, we have a few data centers in New Jersey, all around the East Coast. So we do latency tests that are very similar to the streaming protocol that we use. It's based on UDP. So we do something very similar and then that gives us a number. This is the latency from your client to this specific data center. So this information is one of the first things that we get, the NVIDIA scheduler gets. And then the next thing is the type of user. So by type of user here, I mean, so NVIDIA GeForce Now for gaming, it provides 3 types of subscriptions. One is free, you can play for free. 2 other ones have special permissions, like priority, so you get higher priority to the GPU compared to the free user. Something like the ultimate one is you get the highest, the best GPU that we have, like the 4080 today for your games. So this is one of the inputs. And then the third one is like the game. So not all games need the latest GPU. So we try to, like if you're playing Fortnite, which is one of our popular games on the platform, that dictates also what kind of GPU we need to find. So the last one is the state of the data center. So this is like each data center we have, like in New York, we have a few. They don't have all the types of GPUs that NVIDIA offers. So each data center could have a small subset of the GPUs. Some of them they go back to, I believe, was it? I think Pascal we just removed, I believe. So they go back to based on Ada or Ampere or Turing. That's the one I was looking for. So these types of GPUs, data centers are constructed with different, like it's not the same. We don't have all the GPUs in each data center. So the state of the DC also means what is already taken. If we already have users playing, we need to keep track of how many of those virtual machines are already used, how many are being brought up to be used, and how many of them are not available. And I think Ryan is going to talk about a little bit that use case a little bit more. Our NVIDIA scheduler takes all this information, and I didn't mention it here, but when there's contention, like the peak time usage that we have, the scheduler has to keep track of also how many other users that are also requested the game, like with all of the similar features. So it has to react to that. So some of the constraints that the scheduler works with is the GPU capacity we have is limited. We don't have unlimited capacity everywhere. And then some of it is just not available, like I mentioned. So the scheduler has to know how to react when it's faced with these constraints. So this is a visual of like a 30,000-foot view of what the picture looks like. So you can see there are, like here I'm trying to show like different data centers with different types of GPUs in each data center and where the NVIDIA scheduler sits. So it's very close to our Kubernetes cluster. It interacts with it very frequently to know mainly the state of our clusters. And a lot of this work has to happen even before a user starts streaming. So we do a lot of work just to that's not transparent to the end user. When you play, it just happens. But before that happens, there's a lot of work that needs to happen by the NVIDIA scheduler. So you can see, just trying to illustrate here, two different types of use cases, and then all the data sources that the scheduler has. And then just keep in mind that the scheduler today sits within the data center just to have that close connection with the cluster. So one question that could come up is, let's say a user wants to play Counter-Strike, and then it goes to the DC at the top. If that DC, the scheduler at that in that DC at the top cannot find a virtual machine in that data center, what does it do? Or for example, a user wants to play a game that requires a Turing server at the bottom. So NVIDIA scheduler has to have like a almost live data of what's happening in its data center, but it also has to have an idea of what's happening around it in the neighborhood. So what the NVIDIA scheduler does is it will, if it hits that case where it cannot find a place for a virtual machine for that game, it will try to forward it to the neighboring data center. And this has to still abide by that user location feature of the request. So we don't want to send a user in New Jersey to go stream something from Miami or San Jose or something like that. So it's still the latency based on that latency test that we did at the beginning. We need to make sure that the latency is still acceptable. Sometimes the users still want to play, from a different data center just because they know that the virtual machine is available maybe in Miami. We just display something like, you're gonna see degraded performance, but we don't recommend it, but if you want to go at your own risk, you can go. And then the follow-up question is, what happens if the whole neighborhood doesn't have access to the GPUs? Like if our Kubernetes cluster does not have any capacity, and this happens quite often in the evenings when people come back from work and want to play games. When this happens is we basically queue the requests, and what that means is that the queue, it's not just a single queue, it's we're sharded by the type of user. Like I mentioned, some users have priority because they're paying. Some users want to play a game that requires a specific type of GPU, things like that. So the queue is a little bit, it's kind of a big pipe, but fragmented by type of workload that the scheduler needs to fulfill. So if we don't have capacity at all, then we put users in the queue. So this is something that we try to avoid for paying customers, but it's our backup plan. So we put customers into the queue, and then this also signals to our business unit that, okay, we have more users in Amsterdam. We want to maybe expand our data center in Amsterdam. And that's what's been happening over the past couple of years. So to recap, the scheduler is doing like feature matching by type of workload the request is made. So its main responsibility is to fulfill the request and provide the best GPU resource for the end user. Now, once we have this scheduler that does the feature matching, what we need to focus on next is one of the other challenges that we have is maximizing our capacity in data center capacity the GFN offers. So why do we need to do that? So number one, GPUs are expensive. We have a limited amount of those. And our business unit wants to make sure that the lifetime of a GPU is spent serving the highest priority user. This is data that we look at every day. And like I mentioned, it dictates what the business unit, where it wants to expand. The GeForce now, especially the gaming one, the workload to set it up, it takes a few minutes. So if you want to play a game, you don't want to wait 3 minutes for the machine to start up, for Kubernetes to do its magic and arrange everything. So this plays into that lifetime of a GPU usage, the utilization. And then what we see here, this is actually a snapshot I took from one of our data dashboards. I forget what region it was, but each line is showing the type of GPU usage. So you can see that we have a sinusoidal usage like every day, and this just reflects that people play in the evenings or at nighttime. And then when it becomes like 3 a.m. or something like that, the usage drops. So this begs the question: how do we fill those gaps between those peaks to maximize our capacity? Yeah, I think that's it. So one thing we do is the scheduler that I talked about. One of its other priorities is to fulfill the constraint that the setup takes a few minutes. What we do is we pre-warm GPU workloads in each data center. So what that entails is the scheduler is essentially doing interactions with the Kubernetes cluster to create those VMs and all the resources that are associated with it. And this allows us to achieve that just-in-time feature for game launch. So if you're trying to play a game, all the stuff that I talked about the scheduler really takes like a second or two if everything goes well. And then users are at the menu playing after like 6 seconds. That's what I remember seeing. So the pre-warming helps us with that, where we create those resources. The games are in there, are installed. They can be pulled. And then when the user wants to request a game, they get quick access to the game. And then the scheduler connects the VM with the end user. Let's see. So one of the things that, like I mentioned, the scheduler makes API calls to the Kubernetes cluster to create those resources. And it tracks the state of those resources in the Kubernetes cluster. This informs it when the VM is ready for streaming. So we track the resource state in Kubernetes plus the software that we install on it to make sure that it's ready for streaming. So things like downloading the user's saves in the previous session in the game. If you play the game, we don't want you to start over from the beginning. So that software, we track that as well. So the tracking also tells us the times it takes for this workload setup to happen. And this feeds into a machine learning pipeline that we have that helps us predict the demand. So it connects to the first point. So we predict the demand based on the data we see in the wild, And then that feeds back into the scheduler to tell it, okay, in the next few minutes, I know we're going to get X Fortnite sessions or X Counter-Strike sessions or things like that. This is very crucial for us, and we try to keep an eye on it very closely. But it's also supplemented with like another component that handles sudden demand. Like maybe Fortnite does a patch of the game and new features come in, so more users. Sometimes just predicting based on historical data is not enough, so we do add some like an adjustment in our scheduler just to react to that, and that also feeds on that length, the length of that queue that I mentioned earlier. So the prediction helps us scale our data centers accordingly based on demand, and then for the off-peak times. Okay, so with the off-peak times, what we need to do, we basically use that the remaining capacity for AI workloads. Again, so it's a new product for us, but that's how we use the off-peak time. I think that's it. So for me.
Yep. So I've got, I'll be quick, the last few here. So one of the other challenges we have, maximizing hardware uptime, and this should come to a surprise to no one, but just like every other piece of hardware, GPUs can fail, right? We can we can download a new driver, we can change the driver, try to attach it to a VM, then, right, this doesn't work, right? We come across this all the time. And so this has been a huge problem for us, and something that, like, if you can imagine at our scale, how are we going to be able to manage this? Like, we have driver failures that can happen all the time in real time. How do we get through these things quickly? How do we move past them and get these machines back online, the GPUs working again in the hands of customers? So what we've actually done is, as part of this, is we've worked on a native API in Kubernetes to actually help us coordinate maintenance. And so just to picture what I'm talking about is that what we here are like all these different cases that you come across. I think driver upgrade probably being the most common one that you'll see when you're running your GPU, but all these things that you can come across when you're running your cloud on Kubernetes, all these things that you want to do. And in our situation specifically, we're running these game sessions, right? These are stateful workloads, and we can't just say delete this thing and just send the user on its way, right? The user has paid for a lease for the GPU, so we need to give them their time to play the game. So essentially, the way I would describe this API is it's a way to coordinate maintenance when you have workloads that are non-cloud native, or you can't assume are cloud native. And so this kind of situation is we're no longer talking about pods here. We're talking about situations, right, where I want to get access to this node because the driver failed, and how do I get the machine free so I can actually do work on it? So this is what we've done. We actually have built a maintenance API, and something we're going to open source probably this summer. And this is kind of the summary of what it does. Is we detect a GPU failure. We plan for maintenance, and then we close a node down for maintenance. And so if you imagine, like I said, we have a lease on our GPUs, and we can't just kill the pod and send the user on its way. So what we have to do? Well, we technically have to wait. We have to wait for a little bit. But waiting is expensive, so how can we be really efficient in our waiting? And there's a lot of things, actually, that you can do to be efficient with your waiting. And like Rachid was mentioning, like we do a lot of things where we pre-warm sessions. We put VMs on hosts that are actually not running a game. They're just sitting there waiting for someone to attach. So we have all these opportunities to be really efficient with waiting. And so that's actually what we've done. We've built a finite state machine that allows us to coordinate maintenance, and we have a bunch of sources plug into this so that we can learn all these things about our workload that are going on the node, so that we can be really efficient about, okay, this node is ready for maintenance because it's got a driver failure and there's no workloads on it. So let's go ahead and do maintenance, and we coordinate this at large scale across our entire fleet. This is what it's called. We call it Notify Maintenance. Like I said, it's something the NVIDIA is going to open source at some point this summer. And the whole goal of this is it's just an agnostic finite state machine to coordinate maintenance. Essentially, we call it just a maintenance API. Just like if you were doing maintenance anyway in Kubernetes of your stateful workloads, you would go through all the same steps where you need to coordinate a node, you need to plan a maintenance, you need to wait till it's drained in whatever form that means, and then you need to go and do work on it, and then you need to return it back to the cluster. So all these things are the same thing that you do, and that's all we've done is we've built an API extension to do that, and it works really well for us given our constraints. And then finally, future work. I'll start with the last one. So the like I said, something we want to open source actually because we want it to be a yes. I'm wrapping up. So we want to open source. We want this to be like an API in Kubernetes that people can use for managing their GPU clouds, GPU clusters. When you do maintenance, now everyone's got GPUs in their clouds. They're running their AI workloads. They're running all sorts of different things, and you may or may not have cloud-native applications. And so this kind of thing is what we want to leverage as a solution and for NVIDIA to provide for people that are doing maintenance in Kubernetes. And then
yeah, for the first point, it's just the system is a little bit complex today. The business rules are evolving. We're still manually configuring a little bit our data centers, so we're looking into doing it in autopilot going forward.
Okay, and that's our talk. Thank you very much.
Thank you.